let's make it a little bit more spicy. Let's say -3, 0, and let's say 2.
Okay.
Is that okay?
Yeah, sure.
Good. So now, can anyone give us, through this function, I'm replacing x up here by -3. Then we will get a particular y value. Then we replace x by 0, and we will get a different value, and we'll replace x by 2, and we will get a different corresponding output for the function 4 to the x. So when I plug in -3, what do I get?
For that function?
Of course, that's what you gave me. You want to change the function? No, of course not.
I thought you would.
I won't let you. It's a wonderful function.
1/4.
Very good. 1/64. Awesome. Now let's plug in 0. If you have any questions, stop me at any time, please. 1 indeed. And let's plug in 2.
16.
16. Do we accept these three values? Yes? When we plug in -3, it's 4 raised to -3, which is 1/4 to the third, which is 1/64. When I plug in 0, I get 1. When I plug in 2, I get 16. Now, I want to show you how we go backwards from these values back to these values. Which function will do that? Which function will make 1/64 go back exactly to -3, no other number, and at the same time 1 go back to 0 and no other number, and 16 go back to 2 and no other number? Which function will do that?
Logarithm.
Say it again.
Logarithm.
Correct. The inverse function, right? The inverse function will do that. That's all I wanted for now. Indeed. But I have to convince you that when I apply this function that I'm going to write in a minute, I have to show you why. When we apply it to 1/64, it returns, or the output is what? Negative. Correct. And when I apply this function to 1, the output will be
0.
And when I apply it to 116, the output will be 2. I haven't showed that yet. Okay, very good. So now let's finally come up with a name. The name is a fancy name. We have not seen this before. But not to worry, it's nothing fancy really. But it has log. This is the name of the function. And before I continue, I would like to draw your attention right here. You see this log? And that is a function. So if you go to y equals, and if you put log of x and close the parenthesis, what base is this? It is 10. It shares the same key. That's why the base is 10, although we don't see a base there, right? So as you see, 10 to the x and log are in the same key. So because the base is greater than 1, because it's 10, which of these two shapes I expect to see in the graphing calculator? The one that is increasing on all its domain, or the one that is decreasing on all its domain, and why? I haven't pressed on enter. I did not ask the calculator to graph log. But which of the...
find the one that's increasing because it's greater than 0.
Because the base is greater than 1, not 0.
1.
Yes.
It can't be 0.
Correct. So the base is greater than 1. So it will look like this. Okay, so now I'm ready. I am going to use the standard viewing window, although I know the graph. I'm not going to see anything on the left-hand side of the y-axis. And I claim that this calculator, or the software, and your own calculator is lying to us. Because the function doesn't start here. The function does this. So if you change the viewing window, you will see a better picture. So between -1 and let's say 6, with a scale of 1 is fine. And between -5 and 5, with a scale of 1. Yeah, yes, I saw that. Thank you, thank you. Thank you. -5 and 5 with a scale of 1. So this is a somewhat better graph. Still lying to us. Because see, the calculator says that the function starts here. It does not. So don't trust the calculator. Good. So I haven't finished the name yet. So it's log. Now we have to identify the base. What is the base of this function? Yes, it must be the same base with the base of the exponential function that Tom gave us. So a few minutes ago, he said 4 to the x. Well, the inverse function has to have the same base. If we had chosen 1/3 to the x, then this would have been log base 1/3 of x. Okay? So how do we read this one more time? Log base 4 of x. This is the way we read the function. So one more time, what is this log in there? That's the way the function was defined. So one more time, we read it log base 4 of x. Okay, I still haven't showed yet how I apply this function. So now I can put here logarithmic function. Okay, so I have not shown how I apply this function to 1/64, and the answer is -3, and so on and so forth. Before I do this, together with you, we have to write something very important. Here it is. Very, very important concept in this chapter. I think it's the most important concept in this chapter. I'm going to write first in plain English and then in math, using math. Any log equation can be, oops, didn't mean to write it so far, can be replaced by an exponential equation, comma, and vice versa. Okay, this has to go. So any logarithmic equation can be replaced by an exponential equation, comma, and vice versa. This should not be this close. They're two different words. Okay. Now this was in plain English. Now, how does this translate into math? Here it is. Log base a of x is a number. What type of equation is this? I have a left-hand side, I have the equal symbol, and I have the right-hand side. It must be an equation, because only equations have a left-hand side, equal symbol, and a right-hand side. So what type of equation is this?
Logarithmic.
Right, it is a log equation. Now, this is a very important symbol. It's the double equivalency symbol. What does this mean? It means that this will give us this, or this will give us this. Double equivalency symbol. So please pay attention how we change this into an exponential equation. We have to start with the base. Counterclockwise. A raised to the power y equals x. A raised to y equals x. This is exactly what we wrote in words. A log equation can be replaced by an exponential equation. An exponential equation can be replaced by a log equation. I'm going to use this concept to apply log base 4 to 1/64, log base 4 to 1, and log base 4 to 16, and see what we get. So, log base 4 of 1/64 is a number y. So I'm applying log base 4 to 1/64. So I don't know how to solve this, but I know I can change it into an exponential equation. Can anyone dictate what will be the exponential equation I have to write? Other than Tom. 4 raised to y equals 1/64. Very good. Now I have to think for a moment. As long as, this is an exponential equation, as long as both sides can be presented with the same base, I'm in business. If they cannot be presented with the same base, there is something that we will learn later how to handle, not now. So the left-hand side is base 4. So I'm going to say 4 is 4. What about the right-hand side? Is there a way of writing the right-hand side with base 4? The question is, what will be the power? If I can. If I cannot write it as 4 to a power, then I may not be able to solve it right now.
You can.
Yes. So what will be the power? Say it again.
-3.
-3, right? 4 to -3 is 1 over 64. So now, this is very important. This is an exponential equation. It's the easiest possible one. That's the first level of an exponential equation. I'm not crossing out 4. I'm not simplifying. I can't touch that. I can only think. Two numbers are equal and they have the same base. What has to happen to their exponents? One more time. Two numbers are equal, according to this, and they have the same base. What has to happen to their exponents?
They're equal as well.
They have to be the same. Otherwise, the left-hand side will not equal the right-hand side. See, if I put here 5, 4 to the 5th power will not equal 4 to -3, ever. So if two numbers are equal and they have the same base, the exponents have to be the same. So y equals -3. So we showed that when we apply this function to 1 over 64, the outcome is -3. Agreed? Now I'm going to apply it to 1. So now I have log base 4 of 1 is y. I don't know how to solve this, but I know that any log equation can be replaced by an exponential equation. So how do I write it? Can anyone give us the translation of this into an exponential? And not Tom.
I should have warned you, I'm actually very good at logarithms, at least turning them into exponentials.
Okay, but just don't fall asleep. So 4 raised to y equals, perfect. Again, I have to think now. Well, the left-hand side equals the right-hand side, and I have to think, okay, what number should I have here so that 4 raised to that number is 1? And the only answer is
0.
good. So we show that we applied log base 4 to 1, and we obtained back what?
0.
Yes. And the last one, log base 4 of 16, again, is unknown. But I know how to change this into an exponential equation, and what will be that exponential equation? Can anyone give? Very good. 4 raised to y equals 16. Now I have to make sure that both sides, or if I can, change both sides into the same base. The left-hand side is clear. Although I don't really like non-prime numbers, I'll swallow this one. And the right-hand side is, if I can write it with the same base, then it will not be difficult to figure out. Can I write it with the same? And the power is 2. So remember, we are not simplifying, we are not canceling, I can't touch anything, I can only think. Two numbers are the same, they are equal, and they have the same base. What has to happen to their exponents for this to happen?
Equal.
Yes, so y must equal 2. So then I go back and I say, oh, okay. When I apply log base 4 to 16, I get back 2. So obviously, this is indeed the inverse function of 4 to the x. Now I have a question for you. What do you think if f of x equals 1/2 raised to the x, what will be the inverse function of this? What do you think?
log base 1/2 to the x
of x.
of x.
Correct. What about, let's say, f of x equals log x, and I want its inverse?
10 to the x.
Correct. So this is understood as being 10, like I showed you in the calculator, log. So this is indeed 10 to the x. As we had two different special exponential functions, we have two different log functions. So special log functions. And they are, of course, the ones in the calculator. I'm going to write the exponentials with them as well. So f of x equals log x, which means base 10, and its inverse is 10 to the x. Then f of x equals ln x. It should be nl, natural log, but it's in German, so it's
Yeah, log natural.
log natural, correct. So natural log, and here is common log. And of course, the corresponding f inverse will be
E to the x.
e to the x. So remember, when we see natural log, the base of this function is e. Okay, we'd like to look at a few applications, and also a function with transformations. Let's do that. So let's look at f of x equals negative log x plus 2 and minus 3. Okay, so the question here is asking us to graph the function using transformations. So what would be the first step? Or in other words, what is the base? But not the base of the log or the exponential, but the simplest possible function that was used to create this one.
Log of x.
Good. What is the base? There is no base. What does that mean?
It's 10.
It is 10. Very good. First transformation on the base in order of operations. Yes, awesome. So log x plus 2 left 2. Perfect. Number 2.
Flex
Yes,
the x-axis.
yes, minus log x plus 2 reflect respect to the x-axis. And number 3.
Down 3.
Exactly. Do you all agree with this? Down 3. Okay. So let's start. How do I graph log x? Is it a function? Is it a function that is increasing or decreasing on all its domain?
Base is 10, so it's increasing.
Very good. Where will it cross?
It's
So remember the two shapes. So it's either this shape or this shape. Since the base is greater than 1, it must be this shape. Where does the base function, log function with base 10, pure log function, where will it cross for sure?
10.
Any log function with a base greater than 1 or the base less than 1, if it's the simplest possible one, will always cross at, what is this point?
1, 0.
Exactly. So here's the base, and this is definitely 1. And that is log, common log, x. Good. Next transformation, you told me to shift the graph left 2. But this graph has a vertical asymptote. What do I have to shift first?
Left 2.
The what? What am I shifting first? Left 2.
The x-intercepts.
Nope.
The whole graph.
Nope.
Vertical asymptote.
Yes. So this is x equals 0. Now it will become x equals negative 2. Now I will be shifting the function. This is my marker point. Where will it go? So this is our function log x. So where will this marker go then? I shifted x equals 0 to x equals negative 2. Where will this point go? 2 to the left, right here. So this is the log x plus 2. This is what we've been doing in all functions, correct? With transformations? Are you with me, everyone? Okay, so now I have to reflect. Okay, I'm reflecting with respect to the x-axis. So this is negative log x plus 2. Final step. Final step. What do I do next? Here's my marker. And this is my graph. What do I have to do to it to get the final graph? Very good. So 1, 2, 3. So right here. So this is the final graph. I don't know where it crosses the x-axis. I don't know where it crosses the y-axis. But this is definitely the shape of f of x equals negative log x plus 2 minus 3. Very good. I would like to look at a couple of more problems. And actually, before that, I'd like to identify domain. Domain is a major issue for this function. It's not a friendly function. Domain for log function. So I'm going to choose 3 problems from your book on page 490. So let's say 77 on 490. We're given f of x equals log of 2 minus x. Okay, what type of function is it?
Logarithmic.
It's a logarithmic function. Is the logarithmic function a friendly function?
Nope.
Nope. Nope. It's restricted. I cannot apply it to anything I want. What can I apply it to? Disregard this for a moment. What could I have in here so that log can be applied to it? Say it again. No, but what type of number? What type of number should this be so I can apply log to it?
Any positive number?
Correct. So if it has to be a positive number, then what am I applying log to here? Please read the expression we apply log to.
2 minus x.
2 minus x, which means 2 minus x must be a number greater than 0. This inequality will give us a domain. When we solve this inequality, we will know exactly which x values we can use in this function. So I will move x to the other side. So I have 2 greater than x, and I will be reading it from here. So can anyone give us the domain of this function then? What is the domain of f? It says x less than 2. Because it had negative coefficient. So I have to move it to the other side, and then, so it's x less than 2. To 2 indeed. So this is the domain of this function. So if you want me to evaluate it for some x values, make sure you choose between negative infinity and 2, because if you don't stay within that domain, I will not be able to give you an answer back. So for example, if you say plug in 10, I won't be able to. Because 2 minus 10 is negative 8. The log of negative 8 does not exist. Yes, please.
Where, again, 2 minus x greater than 0, why is that true? Why did
Because
that-
log has to be applied to positive numbers.
I thought that was that's the base and inside, or, like, I thought the base couldn't be.
The base, yes. So the base will never determine the domain.
Okay, domain.
The base is only telling us if the exponential is this or this. And if the log is this or this. It doesn't say anything about the domain. So it only tells us what kind of shape it is. If the base is greater than 1, it will be increasing. If the base is less than 1, it will be decreasing.
Oh, I get it. Yeah.
So the base has nothing to do with the domain. So when I'm trying to identify the domain, I have to look at the expression that log is applied to, no matter what base. Because the idea is the same. If I put here 1/3 as the base, or I put 10, or I put natural log with base e, or I put 1/5, it will not affect the domain. The domain is given by 2 minus x definitely having to be greater than 0.
Domain is inside of parentheses.
Yes,
Got
it's where x is.
Okay.
Very good question. Anything else here? Okay, so let's look at one more. The concept of domain is extremely important. Let's say 76. So we have a function now, which is f of x, log base 5 of x plus 6. Okay, so I'm asked the same question here. I'm asked to find the domain of this function. What will you say? What will you write? What needs to be done?
Need to list the transformations.
Oh, I only want the
base.
domain.
Inequality.
Yes. So what will I write?
X is greater than 6. Not less.
What is log applied to? Please read the expression.
Log base 5,
No, what is log applied to?
x plus 6.
Very good. What type of number must x plus 6 be? Otherwise, I cannot apply log to it.
Positive.
Very good. So then the domain would be
-6 to infinity.
And I have to say that you're right. If you just think in terms of transformations, you will move the graph 6 to the left, and you know where the domain is.
Right.
Correct. Good. Let's look at a word problem now. On page 491, let's look at an application with log functions. Okay, let's say 119 caught my eye. Students in a psychology class took a final examination as part of an experiment to see how much of the course content they remembered over time. They took equivalent forms of the exam in monthly intervals thereafter. So the average score for the group, F of T, after T months, so this is the average score. I take notes when I read the problem. Is given to us as 88 minus 15 natural log t plus 1 for t between 0 and 12. Let's read the problem one more time before we are ready to read the question or questions. Students in a psychology class took a final examination, and then they were tested every month for the next 12 months to see how much they remembered over time. The average score for the group, this is the average score for the group. It's given to us in the form of what type of function? What type of function is this?
Logarithmic.
Good. So if I want to imagine the graph using transformations, is this increasing on all its domain or decreasing on all its domain?
That's 15 log.
15
t
times
plus 1. Okay.
times natural log t plus 1.
13.
Yes. So ln, natural log, is it increasing or decreasing on all its domain?
Increase.
Yes, because the base is greater than 1.
Yeah.
Good. So then the graph will be something like of natural log t will be something like this. This is for natural log t. Then where will I move it in order of operations? I just want to have an idea of how the graph looks like. Where will I move it? I need to graph this. Where will it go?
First is horizontal. So you look
It goes left one. Very good. So this will be the next graph right here. Good. So this will be natural log t plus 1. Then I have to multiply by 15. What will happen to this graph when I multiply by 15? Which transformation is that? 15 out.
Stretching.
Yes. Vertical stretching. Very good. Factor of 15. And then I have a negative.
Reflect.
Reflect. Very good. And then I have up 88. So from 0, it starts at 88. I have an idea of the graph. I'm not asked to do that. I just wanted to have an idea. So it starts at 88, and it continues to decrease. So that's what it is. Good. First question. What was the average score on the original exam? What do I have to determine in order to answer what was the average score for the original exam? I have to find,
0,
say it again.
t equals 0.
Yes, I have to find f of 0. We'll find them in a minute. Part B. We're asked to, what was the average score after 2 months, 4 months, 6 months, 8 months, 10 months, and 1 year? What am I asked to find now? F of 2, f of 4, f of 6, f of 8, f of 10, and f of 12. And then part C, sketch the graph. Okay, so let's put this in the graphing calculator. In y equals, clear if you have anything. So we have 88 minus natural log, no, 15, sorry. 15 natural log, in parentheses x plus 1, we don't have t. And then I go back to second and calc, or I'm sorry, not second and calc, but second and table, and I punch in what I need. Well, I need 0, I need 2, I need 4, and 6, and 8, and 10, and 12. So I put in all those numbers. So 88 first, 71.5, and then 63.9, and then 58.8, and 55, and then 52, and then 49.5. So what do we conclude? What will you say? That it appears that when students take this initially, the psychology exam, what will you conclude then? When they take it initially as a group, the average score was
88.
88% or 88. Good. And then what happens over time?
It decreases.
It decreases. So they take it again every month, but this is what happens. So eventually
Every 2 months.
after a year, it appears that they remember only about half of what they learned in the course. And in order to graph the function, let's do that. We know what to expect. So I know how high will the function go.
88.
Right. How low will the function go?
0. Negative infinity.
How low will the function go? I'm only asked to work on this.
Oh, 12.
How low will the function go? The function, not the x. I know the x has to be between 0 and 12. And the high for y is 88. What will be the low for y? 49.5.
But that's just a loop. Oh,
So that's what I'm going to adjust the viewing window to. So x minimum, 0. X maximum, 12. With a scale of 2. A y minimum, 0. Which should be 50. But let's say we want to see the x-axis. And y maximum, I'm going to put 100. Although it should not be over 88. And with a scale of 20. And I want to graph. And here's the graph. Starting at 88, and when x equals 12, what is this?
49.5.
49.5. Any questions for me? Any questions? Any questions? Okay. The next step, so let me copy the graph here. So 2, 4, 6, 8, 10, 12, and 20, 40, 60, 80, 100. So I'm going to say it starts here, 2, 4, so something like this. And as you see, it's a logarithmic function. We looked at it together, so it's 88 minus 15 natural log t plus 1. And this is t, and this is f. Now, in the next section of chapter 4, we will look at properties of this log function. So there are 3 properties of the log function that no other function has. So 4.3, properties of log. Properties of log. There are 3. Here's the first one. Log in any base apply to a product. X times y. Product can be rewritten as log base a of x plus log base a of y. Notice one thing for a moment here. This is natural log in any base applied to a sum. We have no property for this. We cannot simplify this in any way, shape, or form. So we can simplify or change log applied to a product into a sum of logs, but only if this is a product. So let me give you a numerical example. Like, for example, log base 3 of 5 times 7. Well, this can be written as log base 3 of 5 plus log base 3 of 7. They mean the same thing. What is very important to understand here is that this is a dynamic relationship. So if I start on the left and I get the right, I can start from the right and I get the left. So if I see a sum of 2 logs having the same base, I can change it into log base 3 of the product of 5 and 7. Okay? So it goes both ways. The second property is log applied to a ratio. Log base a of x divided by y. Parentheses are not really required in either case. So then, what do you think this will equal to? Say it again.
Log ax minus log a.
Yes, this will be the difference. Perfect. So this is a quotient or a ratio. So if it's a quotient or a ratio, this can be replaced by log base a of x minus log base a of y. An example would be, so let's say log base 7 of 3 over 9. I'm going to put 19 because I can simplify 3 over 9. So this is the same with log base 7 of 3 minus log base 7 of 19. There is one more property, which is called the power rule. So there is a property for a product, there is a property for a ratio, and there is one more for the power. So log base a of x raised to a power. So this is for a power or power rule. These 3 properties are specific to logs. No other function has these properties. So what we do now, we are moving b right in front as a factor, which means a product. B multiplied by log base a of x. So this is the power rule. There is what it's called, it's not a property, but there is what it's called the change of base formula. So, let me give you an example here before we look in the book. So let's say log base 3 of 5 to the 7th power. this can be rewritten as 7 multiplied by log base 3 of 5. Okay, so last thing before we look at problems is the change of base formula. But this is not a property, this is formula. So change of base formula. Now your calculators are way more sophisticated these days. So with your calculator, if you go to math and scroll down or up, you will see it gives you the option of log base blah blah blah. I personally never cared for it and I never used it. You can use it if you want. However, I prefer working with the bases that are given to us, which is base 10 and base E. So if we are asked to determine, let's say, log base 3 of 7, I can do this by hand. So this is a number, right? What would this change into? What does this really mean?
3 to the 7.
Yes, 3 raised to the y equals 7, counterclockwise. But you and I do not have the capability of determining y. We have no way of determining what power we raise 3 to get 7. If this were 9, meaning both sides of the same base, yes, I can say y is 2. Right, but here I can't. So assuming that we want to get an approximation for log base 3 of 7, we have 2 ways of doing it. And the number will be the same. Because there is only one number that I raise 3 to get 7. I can find 2 different numbers. There is no such thing. The functions are one-to-one. So here's the change of base formula. And I'm changing them into what we have in the calculator, either log, both top and bottom, or ln, top and bottom. The top is always from the number we apply log to. And the bottom is always applied to the previous base. So now when I punch this in the graphing calculator, I have log 7 divided by log 3, or I have natural log 7 divided by natural log 3. And the numbers have to be the same, no matter what. So I get 1.77 approximately. How do I check the answer? What if this 1.77 is incorrect? How would I check?
3 to the power of that should equal 7. If it
Correct.
doesn't, then you got the wrong number.
Correct. Very good. So 3 caret, the previous answer. I don't want to truncate anything. And when I hit enter, I should get
7.
I should get 7. Otherwise, the number is incorrect. If you truncate the number and you just write 3 caret 1.77, of course you will not get 7. You will get very, very close to 7. But if you recall the previous number, the entire number, then the calculator will give you the exact answer. Okay, so what are we doing with these properties? So what is the idea here and what is important?